Before we get into this hellish gauntlet, let's have some ground rules. Specifically, rules for units. To avoid having to determine weight using burgers or distance using Statue of Liberties, we will be using the SI or Standard International Units, since they have official status in nearly every country in the world. For time, seconds. For length, meters. For weight, kilograms. Electric current intensity, amps. Temperature, kelvins. Volume, cubic meters. Energy and work, joule. Pressure, pascals. Amount of substance, moles. And light intensity, candela. Usually they would give out the units for constants, or units would cancel each other out like this equation, but these SI units are best used when in certain exercises they give out complex equations. In 1900, Max Planck published his quantum hypothesis. States that energy can only be transferred in quantized amount. And from that moment, a new branch of chemistry was birthed, quantum chemistry. Now this channel is nowhere intelligent enough to fully explain this topic. It will, however, inform you with the most basics of the subject. As the theory suggests, energy can be quantized, and it can be so in a quanta or photons. Photon is an elementary particle, which are the smallest and are the building blocks for everything. When you look at anything, it can be visible since your eyes perceive photons projected from said things. So basically, photons and light are the same, hence they have the same speed. Photons travel straight, but the electromagnetic field that describes its properties are in sine waves. In this sine wave, the distance between each peak is a wavelength. With that, the amount of peaks that go through a certain point in a second is frequency, and the wave amount is the amount of wavelengths per meter. So almost everything projects photons, but the human eye can only perceive photon wavelengths in the vis or the visible zone, which is approximately 380 to 780 nanometers. Let's get into the formulas. The energy of a photon is calculated using E equals hv equals hc divided by lambda equals hcv swiggle. H is the Planck's constant, 6.626 times 10 by the power of negative 34 joules second, and c is the speed of light, which is approximately 3 times 10 by the power of 8 miles per second. In 1913, Niels Bohr proposed the first quantized atomic structure, describing electrons in defined orbits around the nucleus. Further development of this led to the single electron atom model, which allowed physicists to study the potential energy of an electron and its kinetic energy in relation to the nucleus, laying the groundwork for quantum mechanics. The purpose of introducing the single electron system here is to show you the fundamental basics of quantum chemistry. You ask, what about the multiple electron system? Oh, we'll get there. We'll get there. Now, the energy of an electron in this system is calculated using E equals negative 13.6 times z squared divided by n squared. An electron energy is the sum of its potential and kinetic energy. Since the electron is attracted to the nucleus, the electron has a negative charge and proton have a positive charge, the energy value is negative. Negative 13.6 electron volts, or negative 2.178 times 10 by the power of negative 18 joules, is the ground state energy constant. Z is the charge of the element, and N is the electron orbital. After establishing these two main formulas, we have this relation between wavelength and electron. Hc divided by lambda equals absolute value of negative 13.6 times z squared divided by n squared. It's time we put these theories into practice. Try to solve these exercises. Feel free to pause the video if you want to do it on your own. If not, here's the solution. This exercise starts out simple. 91 megahertz is 9.1 times 10 by the power of 7 hertz. Wavelength equals c divided by lambda. C is the speed of light, which is 3 times 10 by the power of 8 miles per second, and we get the wavelength value of 3.297 meters, or 3.297 times 10 by the power of 9 nanometers, which is way above the visible zone. On to B, the energy is the Planck's constant, multiplied by frequency, so it's 6.626 times 10 by the power of negative 34 times 9.1 times 10 by the power of 7. But this is 0.15 moles of photons. So we add the Avogadro number and the amount of moles. Divide this whole thing by 1000 to get kilojoules, and we get the answer, which is 5.45 times 10 by the power of negative 6 kilojoules. For the second exercise, start by simply applying the formula E equals negative 13.6 times Z squared divided by N squared. We get the energy value of negative 13.6 in electron volts, multiply this by 1.602 times 10 by the power of negative 19, and we get the energy value in joules, which is 2.18 times 10 by the power of negative 18 joules. Quick explanation before we solve this next task. An electron has two states, ground and excited. Ground is when it's in the correct orbital, and excited is when it's not. So how does it get there? By receiving energy, of course. By receiving certain amounts of energy, it allows the electron to overcome the attractive force of the nucleus and jump to a higher level. Vice versa, an electron can also release energy and move down to a lower orbital since it lost the energy to distance from the nucleus. In this case, the photon absorbed by the electron will push it up to n equals 3, or the third orbital. You ask, how then do we calculate the energy required to do so? So we have the ground state energy, E1, added with the photon's energy, Ex, and we get the excited state energy. Ex equals E3 minus E1, which means Ex equals Hc divided by lambda equals negative 2.18 times 10 by the power of negative 18 Z squared multiplied by 1 divided by 3 squared minus 1 divided by 1 squared, and we get the wavelength value of 1.026 times 10 by the power of negative 7 meters. For C, it's basically B. However, what does it mean by ionize the atom? Ionize is losing electrons, so we could interpret the orbital that the electron will jump to as infinite. 1 divided by infinity makes a number so small we could consider that value equals 0, and this is 1 divided by infinity squared we're talking about. So we plug in the numbers onto the formula above, and we get the wavelength value of 9.12 times 10 by the power of negative 8 meters. After this whole ordeal, we understand a little bit more about photons and electrons. However, how do we determine the position of an electron in a model? We will further expand on this subject in our next topic, quantum numbers.